A car-sized object drifting between the stars would be almost impossible to see from Earth. If that object were made of antimatter, seeing it would be the least of our problems. Antimatter is the mirror image of ordinary matter. When the two meet, both are converted into energy, completely. No ordinary impact, no surviving object, just annihilation. Physics tells us antimatter is real. We create it in laboratories, use related processes in medical imaging, and detect it naturally in the universe. But one possibility remains far more difficult to dismiss. Entire stars could be made from it. In 2021, researchers studying data from the Fermi Gamma-ray Space Telescope identified 14 sources with characteristics that made them possible antistar candidates. None has been confirmed, but if even one truly is an antistar, the implications extend far beyond the star itself. Stars can have planets, solar systems can have asteroids and comets, and debris can escape. An antimatter object entering our solar system could resemble an ordinary interstellar visitor until interactions with surrounding matter began giving it away. By then, depending on its size and trajectory, the time available to respond could be dangerously short. The odds of such an encounter appear extraordinarily low, but the deeper mystery remains unresolved. Whether large concentrations of antimatter survived somewhere in the universe, and what could be moving through the darkness between the stars. If space content like this is your thing, we've got plenty more. Subscribe and you'll have a new documentary waiting for you next time you need one. To understand what could be out there, we first need to understand the mirror image of everything we are. At a desk in Cambridge in 1928, Paul Dirac encountered something his mathematics seemed unwilling to let him ignore. The British physicist was trying to reconcile quantum mechanics, the physics governing particles, with Albert Einstein's special theory of relativity. The equations worked beautifully, yet they produced an unexpected second solution. One solution described the electron, a familiar particle carrying negative electrical charge. The other described something stranger. It had precisely the same mass as an electron, yet carried the opposite charge. Nothing matching that description had ever been observed. Dirac initially treated the result cautiously, uncertain whether nature truly contained the particle his mathematics appeared to demand. 4 years later, nature answered. In 1932, American physicist Carl Anderson was studying cosmic rays using a cloud chamber, an instrument that makes the paths of charged particles visible. Inside a magnetic field, Anderson photographed a particle track bending opposite to the direction expected for an electron. Its mass appeared identical, its electrical charge was positive. The mathematical ghost had become physical evidence. The particle became known as the positron, the antimatter counterpart of the electron. Its discovery revealed something profound about the structure of physics. Ordinary particles could possess corresponding antiparticles, sharing the same mass while carrying opposite electrical charge and other reversed quantum properties. The pattern extends beyond electrons. A proton has an antiproton, a neutron has an antineutron. Combine an antiproton with a positron, and you can build antihydrogen, the antimatter counterpart of the simplest ordinary atom. As far as our best measurements can determine, it follows essentially the same physical laws. The crucial difference appears at contact. When a particle encounters its corresponding antiparticle, annihilation can occur. Their mass is transformed into other forms of energy in particles, according to the laws of conservation. For an electron meeting a positron, the result can include energetic photons. Proton and antiproton annihilation is more complicated, producing short-lived particles that rapidly decay into other products. This process releases an extraordinary amount of energy relative to the mass involved. Nuclear reactions convert only a small fraction of participating mass into usable energy. Matter and antimatter annihilation can convert the combined rest mass of an annihilating pair into energy carried by the resulting particles, and radiation and antimatter is no longer confined to equations. The European Organization for Nuclear Research creates and studies antiparticles in particle accelerators, producing extraordinarily tiny quantities under carefully controlled conditions. Hospitals routinely rely on positrons in positron emission tomography, allowing physicians to image processes occurring inside the human body. Even thunderstorms can generate brief flashes associated with antimatter production, high within Earth's atmosphere, so antimatter is real. We create it, detect it, measure it, and watch it obey physical laws that appear universal. That leaves us with a deceptively simple thought. If nature can build individual antiparticles and entire antihydrogen atoms, what prevents it from building something larger? When you look across the galaxy at distant suns, unseen planets, and rocks wandering between stars, how certain can we be that every object is made from the same kind of matter as us? For almost everything in the universe to exist, something had to go wrong. In the earliest moments after the Big Bang, extreme temperatures allowed energy to produce particles of matter alongside their antimatter counterparts. According to the symmetry we might expect from fundamental physics, their quantities should have balanced perfectly. Every particle would eventually have encountered its opposite. Annihilation would have followed, with equal amounts on both sides. Matter and antimatter would have consumed one another until neither remained. The expanding universe would contain radiation, but no enduring atoms to assemble into stars. No planets could form. Chemistry would have no material to work with. Yet you are here. Somehow, the cosmic accounting failed to balance. Current estimates suggest that for roughly every billion matter and antimatter pairs that annihilated, approximately one additional particle of ordinary matter remained. That tiny surplus became the raw material available for everything that followed. Galaxies emerged from it, stars ignited within them, heavy elements formed inside stellar furnaces, and later spread through space. Eventually, some of that surviving matter became planets, oceans, living cells, and observers capable of reconstructing the event. We are built from the remainder. Explaining how that remainder survived became one of modern physics' deepest problems. In 1967, Soviet physicist Andrei Sakharov described three broad conditions that could allow an early universe to develop more matter than antimatter. They became known as the Sakharov conditions. His life carried its own remarkable contradictions. Sakharov helped develop the Soviet hydrogen bomb, then became an outspoken advocate for human rights and nuclear disarmament. In 1975, he received the Nobel Peace Prize. His physics pointed toward a subtle possibility. One necessary ingredient involves charge parity violation, a phenomenon in which certain physical processes behave slightly differently when particles are replaced by antiparticles and spatial directions are reversed. Put simply, nature does not always treat matter and antimatter as perfectly interchangeable mirror images. Experiments have measured this asymmetry in several kinds of particle decay. That seems promising, but there is a serious problem. The amount observed so far appears insufficient to explain the overwhelming dominance of matter across the universe we can see. Something remains missing from our account. That gap reaches into the standard model of particle physics, the framework describing known fundamental particles and three of nature's fundamental forces. Its predictions have survived extraordinarily precise experimental tests. Yet it still cannot fully explain why the early universe left enough matter behind for anything like us to exist. More than half a century after Sakharov framed the requirements, physicists continue searching for additional sources of asymmetry. We know that matter survived. We can observe the result everywhere around us. We still cannot completely explain the mechanism that selected this outcome, and that uncertainty leaves one possibility open. If we do not yet understand why matter gained the advantage throughout the early cosmos, we cannot simply assume every region followed precisely the same history. What if, somewhere among those primordial fluctuations, the balance tipped the other way? Imagine a cloud beginning to collapse where no ordinary atom exists. Its hydrogen is anti-hydrogen. Its drifting nuclei carry charges opposite to those familiar to us. Gravity, indifferent to that distinction, draws everything inward. The cloud contracts, grows denser, and heats under its own weight. Eventually, conditions at the center become extreme enough for nuclear fusion to begin. A star ignites. Such an object could have originated from conditions established during the earliest fractions of cosmic history. The newborn universe was an expanding plasma filled with particles and radiation. Conditions varied across incredibly small regions. Density fluctuated, and the balance between matter and antimatter may also have experienced local variations. Across most of the cosmos we observe, ordinary matter ultimately prevailed, yet some theoretical models allow another possibility. Rare pockets could have formed where antimatter held the local advantage. Size would have mattered enormously. A sufficiently small concentration would encounter surrounding matter and disappear through annihilation. A much larger domain, however, might remain isolated long enough for cosmic expansion and gravitational structure formation to preserve it. Antimatter gas within such a region could later gather into increasingly dense clouds. From there, gravity would follow its familiar script. Antihydrogen could collapse until fusion began inside a growing stellar core. Antihydrogen nuclei would combine through nuclear reactions analogous to those occurring inside ordinary stars, eventually producing antihelium and heavier antielements. Energy released from the core would travel outward and escape as electromagnetic radiation. To your eyes, the result would simply be another star. Its gravity would pull on surrounding objects normally. Its surface could shine at familiar temperatures and colors. The photons reaching our telescopes would carry no obvious label, revealing whether their source contained matter or antimatter. Looking directly at the star would provide remarkably little help. Planet formation could follow as well. A rotating disk of antimatter gas and dust surrounding the young antistar could gradually assemble larger bodies. Grains would become clumps. Clumps would become planetesimals, and some would eventually grow into antiplanets. Leftover material could populate asteroid belts and distant reservoirs of anticometary bodies. Even an ocean on such a world could appear familiar from afar. Antiwater should share essentially the same bulk chemical behavior as ordinary water under equivalent conditions. Clouds could form above its surface. Ice could gather near colder regions. Reflected starlight could give distant oceans the same appearance we recognize from space. The distinction becomes visible where the two cosmic environments touch. An antistar should release a stellar wind containing antiparticles. As that wind encounters ordinary particles drifting through interstellar space, annihilation would produce high energy radiation. Gamma rays emerging from these interactions could therefore provide an indirect fingerprint of an otherwise ordinary looking star. We cannot identify an antistar simply by watching it shine. We must search around its boundaries, looking for energy produced where incompatible forms of matter meet. In 2021, researchers examining observations from the Fermi Gamma-ray Space Telescope reported 14 sources whose properties made that possibility worth investigating. In 2021, 14 points of gamma-ray light acquired an unusual scientific significance. A team led by Simon Duporquet, working with researchers at the Institute for Research in Astrophysics and Planetology in Toulouse, examined years of observations from the Fermi Gamma-ray Space Telescope. Their study, published in the journal Physical Review D, searched for something no confirmed astronomical catalog contained. They were looking for antistars. Since 2008, the Fermi Large Area Telescope has surveyed the sky at gamma-ray energies. These photons carry far more energy than visible light, revealing processes ordinary optical observatories cannot directly observe. The resulting catalogs contain thousands of sources, including pulsars, active galaxies, and other energetic objects. Duporquet and his colleagues searched the Fermi catalog for unidentified sources compatible with gamma rays expected from matter and antimatter interactions near hypothetical antistars. 14 candidates survived their selection. The relevant fingerprint requires some care. When protons and antiprotons annihilate, they commonly produce unstable particles called pions. Those particles decay, creating a characteristic gamma-ray spectrum extending across a range of energies. By comparison, the famous photon energy of 511 kiloelectron volts is associated directly with electron and positron annihilation. For an antistar moving through ordinary interstellar gas, incoming matter could strike antimatter near its surface. Each encounter would feed this broader annihilation spectrum. From Earth, we might therefore detect an unresolved gamma-ray source whose energy distribution resembles the predicted pattern. That is what made the 14 objects interesting. The researchers excluded sources already associated with known classes of gamma-ray emitters. Their remaining candidates displayed characteristics compatible with the antistar hypothesis. Yet compatibility is a long distance from confirmation. Other astrophysical sources could potentially imitate the observed spectra. Some candidates may eventually receive conventional explanations as observations improve. The study therefore treated the 14 objects as antistar candidates, never as 14 discovered antistars. The population estimates were equally cautious. Rather than proving that the Milky Way contains hundreds of thousands of antistars, the analysis used the candidates to establish possible upper limits on how common antistars could be under different assumptions about their distribution. Location matters enormously. An antistar traveling through dense interstellar material should produce more annihilation radiation than one occupying a sparse region. Its velocity, surrounding gas, and distance from Earth would also influence whether Fermi could detect it. So we cannot take 14 unexplained sources and simply multiply them across the galaxy. Still, something important had changed. Scientists now possessed a defined observational method for searching for individual antistars within the Milky Way. The idea could be tested against real measurements, rather than remaining entirely within theoretical cosmology. When you look at those 14 sources, you are therefore looking at unresolved possibilities. None has been confirmed as an antistar. None proves that antimatter solar systems populate our galaxy. But 14 objects passed a search specifically designed to find the gamma-ray traces that such stars might produce. For now, their identities remain open. A planetary system is never perfectly stable. Over immense spans of time, Gravity continually rearranges the smaller bodies moving through its outer reaches. The same principle would apply around an antistar. Antiplanets, following neighboring orbits, would tug on antimatter asteroids and comets. Most disturbances would be tiny, accumulating gradually across millions of revolutions. Given enough time, however, repeated gravitational encounters could radically reshape an orbit. Some objects would move inward, others would be thrown outward until the antistar could no longer hold them. Passing stars could accelerate the process. A stellar flyby within several light years can disturb the distant outskirts of a planetary system. Objects barely bound to their parent star are especially vulnerable. A sufficiently close encounter could scatter large numbers of bodies, sending some into elongated orbits and ejecting others completely. Once released, an antimatter asteroid would become an interstellar wanderer. Its journey would immediately become a contest between distance and erosion. The interstellar medium, meaning the diffuse gas and dust occupying the space between stars, is extremely sparse by earthly standards. Yet it is not empty. In many regions, hydrogen atoms remain scattered throughout that apparent emptiness. Every ordinary particle striking an antimatter surface creates an opportunity for annihilation. An exposed object would therefore lose material continuously as it traveled. The exact erosion rate would depend on several factors, including its velocity, composition, size, and the density of the region it crossed. A small fragment moving through relatively dense interstellar gas could disappear far sooner than a massive body following a path through thinner surroundings. Space itself varies enormously. Dense molecular clouds contain far more material than the diffuse regions between stars. Hot ionized environments can be thinner. Beyond galaxies, some cosmic regions reach densities vastly lower still, although such environments would not describe most journeys between neighboring stars inside the Milky Way. For an antimatter object traveling within our galaxy, survival therefore depends heavily on its route. Size provides another advantage. As an object grows, its volume increases faster than its surface area. More mass becomes stored behind each exposed portion of the exterior. Annihilation can steadily consume the outside while leaving deeper material untouched for longer periods. You can picture the surface becoming a sacrificial boundary. Incoming atoms strike the exterior and vanish with corresponding antimatter. Energy escapes from the interaction while the object gradually loses mass. A tiny grain offers little material to surrender. A large asteroid or comet possesses a substantial interior reservoir. Over millions of years, that difference matters. Any antimatter debris capable of crossing significant interstellar distances would need to survive countless encounters with ordinary particles. Smaller fragments face the greatest difficulty. Larger bodies have better odds, particularly if their trajectories remain within unusually sparse regions. This naturally shifts attention away from microscopic grains and towards substantial objects. An antimatter comet or asteroid, formed far from its parent antistar and later expelled by gravitational disruption, could carry enough mass for its exterior to erode while preserving part of its core. The threat, if such objects exist at all, would therefore emerge through ordinary celestial mechanics acting upon extraordinary material. Gravity provides the escape, interstellar space determines survival, and immense size may provide the endurance required to travel between the stars. Suppose a new point of light appears on an observatory image tonight. It moves slightly between exposures, enough for software to recognize an object crossing the background stars. Astronomers calculate its trajectory. The orbit is hyperbolic, revealing that it came from interstellar space. Nothing about the image reveals what it contains. An antimatter asteroid, illuminated by the sun, should reflect photons much like an ordinary asteroid with comparable surface properties. Its brightness could reveal approximate size and reflectivity. Repeated observations could determine speed and direction. Yet visible light alone would not announce that its atoms carried the opposite identity. The Vera Rubin Observatory searches enormous regions of sky for changing objects. Panoramic Survey Telescope and Rapid Response System performs repeated surveys for asteroids and other transient sources. The Catalina Sky Survey searches specifically for near-Earth objects. Each could discover the visitor. None could identify antimatter from an ordinary optical image. The distinguishing evidence would come from high-energy radiation produced as ordinary particles encountered the object's surface. Closer to the sun, the solar wind supplies a continuous stream of charged particles. An antimatter body passing through that stream could generate increasing annihilation radiation as the surrounding particle density rose. But recognizing that signal presents another challenge. Gamma ray observatories were designed primarily to study distant cosmic sources rather than provide continuous real-time tracking of nearby antimatter objects. No dedicated planetary warning network currently surrounds the Sun with instruments optimized specifically for this task. Consider how quickly an interstellar visitor can move. The interstellar comet 3I Atlas was discovered in July 2025 while already traveling through the solar system. Its incoming speed relative to the Sun was roughly 130,000 miles per hour. At such velocities, astronomical distances shrink rapidly into human timescales. From Jupiter's average orbital distance of roughly 5 astronomical units, a hypothetical object traveling directly toward Earth's region at a comparable speed could cover that distance in roughly 5 to 6 months. Geometry would determine the actual encounter time, but the scale illustrates the problem. Detection is only the beginning. Astronomers must gather additional observations, refine the orbit, identify the object's composition, and determine whether its path presents any danger. For a fast interstellar body, each step unfolds while the object continues, crossing millions of miles. Ordinary planetary defense benefits from familiarity. The asteroid Apophis, roughly 1,100 feet across, has been observed repeatedly for decades. Successive measurements refined its trajectory until astronomers could exclude an impact with Earth for at least a century. A newly arriving interstellar object offers no such history. If that object were antimatter, optical surveys might still track it successfully while remaining unaware of its composition. Only an unusual high-energy signature could reveal what sunlight could not. So the detection problem contains a strange divide. We might see an object approaching and know exactly where it is, yet still misunderstand what we are watching. The danger would remain hidden inside, something that, through an ordinary telescope, could look completely familiar. Earth's atmosphere begins gradually, with no sharp boundary separating air from space. Hundreds of miles above the surface, isolated particles already drift along an incoming object's path. For ordinary meteors, these first encounters barely matter. For antimatter, each contact is fundamentally different. Annihilation begins immediately. A nitrogen nucleus or oxygen nucleus striking the antimatter surface can interact with corresponding antiparticles. Proton and antiproton encounters generate unstable particles, including pions, which decay through several pathways. The resulting particle shower can contain gamma rays, electrons, positrons, muons, and neutrinos. The process intensifies during descent. Around 60 miles above Earth, The atmosphere remains extremely thin, yet its density increases rapidly downward. More particles begin striking the exposed surface every second. Each interaction removes some antimatter while releasing energy into the surrounding atmosphere. An ordinary meteor also loses material during entry. Atmospheric compression and intense heating can melt, vaporize, and fragment its surface. Its kinetic energy drives the familiar luminous trail we see crossing the night sky. An antimatter body adds annihilation energy to that process. Instead of waiting for a physical collision with the ground, energy production follows the object throughout its atmospheric path. The leading surface encounters increasingly dense air, generating a descending region of energetic particles and radiation. Depending on the object's size and velocity, much of its mass could be consumed before reaching lower altitudes. Gamma rays would be among the important products, though their behavior depends strongly on energy. Some would interact with atmospheric particles and feed secondary particle cascades. Others could travel substantial distances before depositing energy. Muons produced within the shower can penetrate deeply through matter, while neutrinos would pass through Earth with little interaction. You would therefore have no single impact point where the event truly begins. The atmosphere itself becomes part of the interaction. As energetic radiation and charged particles spread through surrounding air, they ionize molecules, stripping away electrons and creating electrically charged regions. A sufficiently energetic event could disturb atmospheric electricity and potentially affect communications or electronic systems. The exact scale of any electromagnetic effects would depend on altitude, geometry, total energy, and how rapidly that energy was deposited. Predicting a continent-wide electromagnetic pulse would require detailed modeling, so its magnitude cannot be assumed from annihilation energy alone. Still, the underlying distinction remains severe. An ordinary asteroid carries a finite reservoir of kinetic energy determined by its mass and speed. An antimatter object carries that same kinetic energy while also possessing the potential to release annihilation energy whenever its material encounters ordinary matter. Every layer of atmosphere provides more of that matter. The object loses itself as it descends, atom by atom, while the surrounding air participates in the same destruction. If the antimatter body is small enough, the atmosphere may consume it completely at altitude. If enough survives, interaction continues into progressively denser air and potentially the surface. There is no separate interval between arrival and energy release. For antimatter entering Earth's atmosphere, contact itself starts the event. Start with the weight above your head. At sea level, each square foot of Earth's surface supports roughly 2,100 pounds of atmosphere. Extend that square foot upward through the entire atmosphere, and the air above it weighs about as much as a small car. Most of that mass lies within the lower reaches, compressed downward by gravity. Now place an antimatter body on a steep path through it. Every pound of air encountered removes some antimatter through annihilation. Whether anything reaches the surface depends on the object's shape, trajectory, density, fragmentation, and the way annihilation energy alters the surrounding flow. A simple straight column calculation can illustrate the scale, although it cannot reproduce the full physics of atmospheric entry. Consider a rocky antimatter object roughly 10 feet across in each dimension. If its density resembled an ordinary chondritic meteorite, its starting mass would be around 200,000 pounds. That sounds enormous. Yet a body 10 feet wide presents a frontal area near 100 square feet. A vertical atmospheric column covering that area contains roughly 210,000 pounds of air. In the simplest one for one annihilation picture, There is enough atmospheric matter along that path to consume an antimatter object of comparable mass before it ever touches the ground. The atmosphere, therefore, changes the calculation dramatically. To imagine material surviving, we must alter the assumptions. Perhaps the object is denser. Perhaps its trajectory and interaction create complex shielding effects. Perhaps annihilation products push surrounding gas away from portions of the surface. These possibilities require detailed hydrodynamic and particle transport modeling before anyone can assign a reliable, surviving mass. But suppose, purely as a scale exercise, that about 1,340 pounds of antimatter somehow remained when it reached ordinary matter at the surface. An equal mass of terrestrial material could annihilate with it. Energy equals mass multiplied by the speed of light squared, then gives an energy release near 109 quintillion joules from the combined mass conversion. For comparison, the Soviet Union tested the Tsar Bomba in 1961. Its explosive yield was about 50 megatons of trinitrotoluene equivalent, corresponding to roughly 210 quadrillion joules. The hypothetical surface annihilation would therefore release roughly 500 times that energy, not 5,000. And this still ignores energy deposited during atmospheric descent. You can see why precision matters here. A small change in surviving antimatter produces an enormous change in released energy. Geometry matters. Atmospheric interaction matters. The fraction that survives matters most of all. The image of a concert grand piano is useful only as a mass comparison. Roughly 1,300 pounds of antimatter reaching the surface would represent an extraordinary energy reservoir. Yet, whether a garden shed-sized antimatter object could actually deliver that surviving mass cannot be established by subtracting a single atmospheric column from its starting weight. The arithmetic is simple. The journey through real air is not. Scale changes this problem faster than intuition can comfortably follow. Take an antimatter body roughly 33 feet across, comparable to a large house. If its density resembled ordinary chondritic rock, a spherical object of that diameter would contain several million pounds of antimatter. Its exact atmospheric behavior would depend on fragmentation, trajectory, velocity, and the interaction between annihilation products and incoming air. Even so, size provides an important advantage. Volume grows faster than surface area as an object becomes larger. The exterior is where incoming atmospheric particles interact first, while increasing amounts of mass remain deeper inside. A larger antimatter body, therefore, carries proportionally more material behind each square foot of exposed surface. Increase the diameter to roughly 164 feet, within estimates often discussed for the Tunguska impactor. An atmospheric entry becomes vastly more energetic. An ordinary object of this scale can already devastate a large region through an airburst. An antimatter equivalent introduces an additional energy reservoir through annihilation. The consequences cannot be reduced to a simple blast radius. High-energy particle cascades would deposit energy throughout the atmosphere. Gamma radiation could alter atmospheric chemistry, including reactions affecting ozone. Thermal effects and pressure waves would depend strongly on altitude and energy deposition. Claims of hemisphere-wide ozone destruction or firestorms spanning millions of square miles require detailed modeling that does not currently exist for such hypothetical events. Now increase the scale again. An antimatter asteroid roughly 6/10 of a mile across would contain an enormous rest mass energy reservoir. If a substantial fraction eventually annihilated with ordinary matter, the released energy would exceed familiar impact events by extraordinary margins. Yet, comparisons with the Sun require care. The Sun radiates roughly 380 septillion joules every second. Even complete annihilation of a rocky antimatter asteroid 1 kilometer across would fall far short of several days of total solar output. The event would still be catastrophic. At roughly 6 miles across, comparable in diameter to the Chicxulub impactor, the numbers become larger again. An ordinary asteroid of this scale helped trigger a global mass extinction about 66 million years ago. An antimatter counterpart could, in principle, release vastly more energy if significant mass survived long enough to annihilate with Earth. Would that destroy the planet itself? Probably not in the literal sense of overcoming Earth's total gravitational binding energy. Breaking the entire planet apart requires energy on a scale far beyond even a 6-mile antimatter asteroid. But global habitability and planetary survival are very different thresholds. An event can leave Earth gravitationally intact while radically transforming its surface, atmosphere, and biosphere. These calculations describe hypothetical objects. They are not predictions, warnings, or evidence that anything comparable is approaching us. Their value lies elsewhere. When we follow the physics honestly, scale reveals how quickly annihilation energy grows with mass. Energy equals mass multiplied by the speed of light squared remains indifferent to whether the mass exists in a laboratory, inside an equation, or within some undiscovered object between the stars. The mathematics sets the boundary of what nature permits. Our task is simply to read it accurately. At 7:17 in the morning, on June 30th, 1908, the Siberian sky erupted. Something had entered the atmosphere above the remote region near the Podkamennaya Tunguska River. Witnesses described a brilliant object crossing the sky, followed by intense heat and a tremendous atmospheric blast. People tens of miles away felt the effects. Then came the pressure wave. Across roughly 830 square miles of forest, an estimated 80 million trees were flattened. Their trunks formed broad radial patterns extending outward from the region beneath the explosion. Yet at the center, investigators would eventually confront an unexpected absence. There was no enormous impact crater. That discovery took years to reach. The Tunguska region was extraordinarily remote, and political upheaval further delayed scientific investigation. In 1927, Russian mineralogist Leonid Kulik finally led an expedition into the devastated landscape. Kulik expected evidence of a conventional meteorite impact. A crater should mark the collision site. Large fragments might remain embedded in the ground. Instead, the expedition encountered scorched and fallen forest without the obvious impact structure they had anticipated. The mystery persisted for decades. Researchers proposed comets, asteroids, unusual atmospheric explosions, and increasingly exotic possibilities. One arrived directly from particle physics. In 1965, Clyde Cowan, Chandra Raju Atluri, and Willard Libby published a paper in the journal Nature examining whether an antimatter meteor could explain Tunguska. The idea had an appealing feature. If antimatter encountered the atmosphere and annihilated during descent, the incoming body might leave little conventional material behind. For an event lacking a crater, that possibility deserved consideration. But later evidence increasingly favored an ordinary cosmic impactor undergoing an atmospheric airburst. Researchers identified microscopic particles in the region that were consistent with extraterrestrial material. Modern computer simulations also demonstrated how a rocky asteroid could fragment and release tremendous kinetic energy above the surface. An airburst does not require a crater. At sufficient speed, atmospheric forces can disrupt an asteroid before ground contact. Its energy is transferred into the atmosphere, producing blast effects across a wide area while leaving relatively little recognizable debris. This mechanism fits the observed tree patterns and much of the physical evidence from Tunguska. Today, the scientific consensus strongly favors a natural asteroid or cometary body, with a stony asteroid commonly considered the leading explanation. The antimatter proposal, therefore, became unnecessary. That distinction matters when we examine the history of the case. Science did not establish antimatter as the cause, and current evidence provides no compelling reason to invoke it. Yet, the episode demonstrated how incomplete observations can leave radically different mechanisms competing for attention. Imagine investigating Tunguska with only eyewitness accounts, flattened trees, and no crater. Without modern particle detectors or comprehensive atmospheric monitoring, how would you identify the exact nature of something that vanished during its descent? For decades, researchers could not. The Tunguska mystery narrowed as evidence accumulated and modeling improved. Its conventional explanation became increasingly persuasive, while the antimatter hypothesis faded into scientific history. The case, by every reasonable standard, is closed. Probably. Among the possible forms an antimatter visitor might take, a comet offers a particularly useful model. Comets are built to lose material and keep moving. Their survival depends partly on size, partly on composition, and partly on how their outer layers respond as conditions change around them. An ordinary comet approaching the Sun begins shedding volatile material. Surface ice turns directly into gas through sublimation, carrying dust outward and producing the familiar coma surrounding the nucleus. Much of the body remains protected beneath that active surface. Large comets can endure repeated passages while gradually losing mass. An antimatter comet would face a different process. As it entered the solar system, particles from the solar wind would encounter antimatter across its exposed surface. Each contact would produce annihilation, steadily removing material. The interaction would intensify closer to the Sun because the solar wind becomes denser inward. Yet increased annihilation could introduce another effect. At sufficient mass and activity, the energy emerging around the surface may alter the immediate environment surrounding the body. Radiation and charged particles generated by annihilation could create outward pressure, reducing how efficiently incoming solar wind particles reach fresh antimatter. In principle, this could provide partial self-shielding. The comparison with an ordinary comet is imperfect but useful. A conventional comet develops an extended coma and ion tail as sunlight and the solar wind interact with escaping material. An anticomet could instead become surrounded by energetic annihilation products. Its most revealing emission would appear in gamma rays. Some theoretical estimates place potentially relevant masses between roughly 200 million and 20 billion pounds. That range corresponds to bodies substantial enough for their interiors to survive longer while their outer layers are consumed. The exact threshold would depend strongly on composition, geometry, velocity, and the surrounding particle environment. From Earth, the contrast between observing methods becomes crucial. Optical telescopes could see sunlight reflected from the approaching body without revealing whether its material was ordinary matter or antimatter. Gamma ray instruments, however, might detect an increasingly energetic source associated with annihilation. The source could brighten as solar distance decreased. A useful, real example of how interstellar objects challenge interpretation arrived with the discovery of the interstellar comet 3 I Atlas in July 2025. Like other active comets, its trajectory could be influenced by non gravitational forces produced as material escaped its surface. Such acceleration does not imply anything exotic. Ordinary cometary outgassing can alter motion without gravity being responsible for every observed change. For a hypothetical anticomet, asymmetric annihilation could also exert force. Its direction and intensity might differ from conventional outgassing, potentially offering another diagnostic alongside gamma ray observations. Detecting that combination would require instruments capable of recognizing the pattern while enough time remained to study it. That makes the anticomet an especially consequential hypothetical case. A sufficiently massive body might preserve more of its interior during the journey inward, even while announcing its unusual nature through growing high energy emissions. If recognized early enough, we might receive weeks or months of evidence. The question would be whether we understood what we were seeing. Far beyond the planets, the architecture of our solar system becomes something we have never directly seen. The Oort cloud is thought to form a vast spherical reservoir around the Sun, beginning roughly 2,000 astronomical units away and perhaps extending outward to 100,000 astronomical units. At that outer boundary, the Sun would appear as one bright star among countless others. Its gravity still reaches across the distance, yet its influence is extraordinarily weak. Objects there may require millions of years to complete a single journey around it. Astronomers estimate that this distant reservoir could contain roughly 2 trillion bodies. They are thought to include comets, icy planetesimals, and other remnants left from the solar system's formation approximately 4.6 billion years ago. Yet no telescope has ever directly observed a confirmed Oort cloud object residing there. We know the region through inference. Long period comets sometimes arrive from immense distances on stretched orbits that point toward such a reservoir. By reconstructing their trajectories, astronomers can estimate where these bodies originated. The cloud itself remains beyond the practical reach of current surveys. Its isolation also makes it vulnerable to passing stars. During the Sun's 4.6 billion year history, numerous stellar encounters have altered the gravitational environment surrounding the outer solar system. A passing star does not need to collide with anything. Its gravity alone can disturb distant objects, changing orbits that had remained stable for enormous spans of time. One particularly close encounter involved Scholz's star, a faint red dwarf accompanied by a brown dwarf. Roughly 70,000 years ago, the system passed about 0.82 light years from the Sun, carrying it through the broader region associated with the Oort cloud. Such encounters can redirect distant bodies inward. Because their journeys are so long, gravitational disturbances created thousands of years ago may still be producing consequences today. An object displaced at the cloud's edge can spend ages falling toward the planetary system. Now consider the antimatter possibility within that framework. If even one ancient stellar encounter involved an antistar system, gravitational interactions could theoretically have exchanged material between distant reservoirs. Antimatter comets or asteroids disturbed during such an encounter might have entered extremely remote solar orbits, where surrounding matter is sparse enough for erosion through annihilation to proceed very slowly. Nothing confirms that this happened, but our observations cannot currently exclude individual exotic objects hidden among trillions of ordinary ones. We cannot inventory the Oort cloud because we cannot directly see its population. Even its estimated boundaries and total number of objects remain models built from indirect evidence. When you picture the solar system, then, the familiar planets occupy only its innermost neighborhood. Beyond them stretches an enormous volume whose contents are largely unmeasured. We infer what circles there from the occasional object that falls inward. Most are almost certainly ordinary ice and rock. Yet across that immense unseen population, our instruments cannot presently examine every body and determine what kind of matter it contains. Probability changes the character of this scenario. Physics may permit an event while the universe makes its occurrence extraordinarily unlikely. To understand where an antimatter impact belongs on that spectrum, we have to separate possibility from evidence. The 14 antistar candidates identified in Fermi Large Area Telescope data provide an upper limit, not a confirmed population. Under assumptions used in the analysis, researchers estimated that antistars in the Milky Way's disk could be rarer than roughly 1 for every 400,000 ordinary stars. Even that would leave enormous distances between potential systems across a galaxy roughly 100,000 light-years wide. Statistically, the nearest candidate population would therefore remain hundreds of light-years away. For antimatter debris from such a system to enter our neighborhood, gravitational circumstances would have to align with exceptional precision. A close stellar passage offers one conceivable route. The antistar would need to approach sufficiently near the Sun for its gravity, or interactions between distant reservoirs of orbiting material, to transfer antimatter bodies onto trajectories connected with our solar system. Such close encounters are rare already. Requiring the passing star to be an antistar makes the combination vastly less probable. Over the Sun's 4.6 billion year history, many stars have passed through its broader galactic neighborhood, yet no confirmed encounter involved antimatter. Given the stringent observational limits on nearby antistars, the probability that a sufficiently close historical visitor belonged to such a population appears extremely small. Survival creates another filter. Any antimatter body transferred billions of years ago would spend that immense interval encountering ordinary particles. Even the sparse hydrogen found between stars and throughout the outer reaches of planetary systems would gradually consume exposed antimatter. Smaller bodies would disappear first. Only sufficiently massive objects, protected by their own depth of material, could plausibly endure such prolonged erosion. Then comes the inner solar system. As an antimatter object approached the Sun, interactions with increasingly abundant ordinary particles should strengthen its high-energy emissions. Gamma-ray observatories could potentially detect such unusual activity, although identifying a moving source and proving an antimatter origin would require careful analysis. Since 2008, the Fermi Large Area Telescope has repeatedly surveyed the gamma-ray sky. No confirmed moving antimatter object has been identified within our solar system. That is meaningful evidence for present safety. So if you ask how seriously scientists regard an antimatter impactor, the answer is straightforward. This is not treated like a known near-Earth asteroid hazard. Planetary defense programs actively track ordinary asteroids because those objects demonstrably exist nearby and sometimes cross Earth's orbit. Antimatter impactors remain hypothetical. Distance works against them, rarity works against them, erosion works against them. Together, those barriers push the scenario toward extreme improbability. Yet examining it remains scientifically valuable because possibility and probability answer different questions. The exercise exposes where observation ends, where inference begins, and how much of our confidence depends on what our instruments can actually measure. The most useful response to an improbable cosmic hazard is measurement. You do not need certainty that something exists before improving the instruments capable of finding it. In the case of antimatter, several observatories already collect pieces of the necessary evidence, even though none was built specifically to search for an incoming anticomet. The Fermi Large Area Telescope remains central to that effort. Operating since 2008, it continues surveying the gamma ray sky and expanding the database against which unusual sources can be compared. Each additional year provides more observations of the 14 antistar candidates reported in 2021, allowing researchers to test whether their emissions remain compatible with proposed antimatter signatures. Other facilities extend that reach differently. The Cherenkov Telescope Array Observatory is being developed with telescope arrays in Chile and on La Palma in the Canary Islands. It will study extremely energetic gamma rays, with sensitivity exceeding previous ground-based instruments across important portions of its observing range. Although its primary science extends far beyond antimatter, unexpected high-energy sources can still become part of that broader search. Visible light provides another essential layer. The Vera Rubin Observatory in Chile released its first imagery in 2025 and is designed to repeatedly survey the southern sky with extraordinary depth. Its legacy survey of space and time will detect changing and moving objects across enormous areas, improving our ability to discover interstellar visitors and calculate their trajectories. An ordinary-looking point of reflected sunlight could therefore gain context rapidly. If gamma-ray instruments independently recorded unusual emissions from the same moving coordinates, astronomers would have something far more interesting. Combining optical orbital measurements with high-energy observations could distinguish an unfamiliar physical process from conventional cometary activity. Proposed future missions could sharpen this capability further. The all-sky medium-energy gamma-ray observatory concept has been developed to improve sensitivity in the medium-energy gamma-ray band, where important signatures from nuclear processes and particle interactions appear. Instruments operating in this range could help investigate phenomena that current observatories cannot characterize with equal precision. None of these systems constitutes a dedicated antimatter warning network. A purpose-built architecture could, in principle, place specialized gamma-ray detectors on spacecraft distributed through the inner solar system. Multiple observing locations would help establish whether a source was moving, determine its trajectory, and compare its changing emissions with its decreasing distance from the Sunday. Secondary payloads aboard suitable missions might reduce costs compared with launching an entirely independent fleet. Such a network has not become a planetary defense priority. The evidence does not currently justify treating antimatter objects like established asteroid hazards. But the observational landscape has changed. The antistar candidates reported in 2021 gave astronomers specific sources that can be tested rather than a purely theoretical population. For us, that is where the science becomes most productive. Better instruments need not assume the extraordinary explanation. They simply expand what we can measure, allowing nature itself to narrow the possibilities. Imagine a world where nothing appears unusual. Dawn arrives over an ocean. Clouds gather above continents. Mountains rise through moving crust, while a magnetic field extends into space. From orbit, you might study this planet for years without recognizing the profound difference beneath everything you see. Every atom there could be antimatter. The fundamental forces would allow such a world to behave remarkably like ours. Gravity would pull an antiplanet into a sphere and keep it circling its antistar. Electromagnetism would bind anti-electrons to antinuclei, creating antiatoms with familiar chemical properties. The strong nuclear force would hold their nuclei together. At the center of the system, an antistar could fuse antihydrogen into antihelium. Its interior pressure, luminosity, temperature, and lifetime would follow the same stellar physics governing ordinary stars of equivalent mass. Photons leaving its surface would carry no label identifying their origin. To us, it would simply shine. Around it, antimatter dust could accumulate into larger bodies through collisions and gravity. An antiplanet might separate internally as it heated, producing an anti-iron core beneath layers of antisilicate rock. Convection could drive geological activity. A rotating conductive core could generate a planetary magnetic field. Anti-water could collect in oceans. Seen remotely, those oceans would reflect light through the same electromagnetic interactions that shape the appearance of ordinary water. An atmosphere could scatter shorter wavelengths. Weather systems could circulate energy between warm and cold regions. Chemistry would proceed according to familiar principles, only with every constituent particle replaced by its antimatter counterpart. Then biology enters the thought experiment. If life's emergence depends on complex chemistry, usable energy gradients, and molecules capable of storing and reproducing information, antimatter chemistry offers no obvious fundamental prohibition. Anti-carbon could form elaborate molecular structures. Antiproteins could perform chemical functions. Anti-deoxyribonucleic acid could, in principle, encode inherited information. Evolution would still operate. Replication would produce variation. Environments would impose selection. Successful organisms would leave more descendants. Natural selection has no requirement that biological matter carry one particular sign of electrical charge. Given enough time, intelligence might emerge there too. Such a civilization could study gravity, electromagnetism, and quantum mechanics. Its physicists might derive the same equations Paul Dirac developed in 1928. Their mathematics would reveal particles identical in mass to their familiar particles, yet carrying opposite charges. They might manufacture a few experimentally. From their perspective, those strange particles would be antimatter. Their astronomers could map a galaxy filled mostly with stars resembling their own. Perhaps their gamma-ray catalogs would contain a handful of unexplained sources, possible stars composed of the opposite kind of matter. They might debate whether entire ordinary matter systems could exist somewhere beyond their reach. They would measure the same universe we do. Only direct contact would expose the difference. At that boundary, the symmetry would become absolute in another sense. Neither side would survive the encounter unchanged. Matter and antimatter would annihilate together, with physics granting no preference to either. Each civilization would consider itself ordinary, and each would be correct. For more than half a century, the Fermi paradox has rested on a simple contradiction. The Milky Way contains billions of worlds where life might develop, yet we have found no confirmed evidence of another civilization. Distance offers one explanation. Extinction offers another. Perhaps, however, some civilizations could be separated by something deeper than either. The dividing line might be matter itself. If large regions of the universe contain antimatter, civilizations arising there would face a barrier, unlike ordinary interstellar distance. A spacecraft built from matter entering an antistar system would encounter particles streaming outward from the star. Each collision between matter and antimatter would produce annihilation, gradually consuming the vehicle while releasing energetic radiation. No ordinary shield solves that problem. Any protective material made from matter would face the same interaction. Magnetic fields might redirect charged particles, but neutral antimatter and sufficiently energetic encounters would remain hazardous. Reaching an anti-world physically could therefore demand technologies beyond anything known to physics today. For an antimatter civilization, our neighborhood presents the identical obstacle. Their explorers could cross empty interstellar regions, only to face increasing destruction upon entering a matter-dominated stellar environment. From their perspective, our solar wind would be the dangerous one. Our planets would be unreachable surfaces. Even collecting a physical sample could become an extraordinary engineering problem. But information can cross the boundary. Photons, the particles carrying electromagnetic radiation, are their own antiparticles. They travel through matter and antimatter without undergoing mutual annihilation simply because they encounter either one. Radio transmissions could cross the divide, so could laser pulses and gamma rays. Two civilizations might therefore communicate across a boundary neither could safely cross. The search for extraterrestrial intelligence has spent more than 60 years examining the sky for possible technological signals, especially at radio and optical wavelengths. Gamma ray observations provide another potential channel. Yet, searches have generally not focused on a deliberate annihilation beacon centered around the characteristic energy produced when electrons and positrons destroy one another. That energy is 511,000 electron volts. Any civilization familiar with particle physics would recognize its significance. A deliberately modulated signal near that energy could carry an unmistakable implication, especially if repeated with mathematical structure. Matter physicists would understand it. Antimatter physicists would understand it too. Then there are the unexplained signals already recorded. On August 15th, 1977, the Big Ear Radio Telescope detected the 72-second burst, later called the WOW signal. It came from the general direction of Sagittarius and has never been conclusively explained or observed again. More recently, discussions surrounding the interstellar object 3I Atlas noted a broad directional proximity between its incoming path and the region associated with that signal. There is no evidence connecting them. The alignment is overwhelmingly likely to be coincidence. Still, the larger possibility remains scientifically intriguing. Perhaps intelligence does not always fail to cross the distances between stars. Some civilizations might exchange information while remaining forever physically separated, able to see one another across the galaxy, yet unable to meet without destroying exactly what they came to find. Some mysteries endure because the evidence is incomplete. Others endure because the evidence is unusually precise. The WOW signal belongs to the second category, a single recorded event that has remained suspended between confirmed observation and unresolved explanation for nearly half a century. On August 15th, 1977, the Big Ear Radio Telescope at Ohio State University was scanning the sky when it recorded an extraordinary burst. Astronomer Jerry Eman later examined the computer printout and noticed the sequence marking its unusual intensity. He circled the characters and wrote one word beside them: "Wow." The name remained. The signal lasted 72 seconds, matching the time a fixed celestial source would remain within the telescope's observing beam as Earth rotated. Its frequency lay close to 1,420 megahertz, associated with neutral hydrogen, the most abundant element in the universe. Astronomers had long considered this region of the radio spectrum interesting for interstellar communication. Its narrow frequency range made the detection particularly unusual. Natural cosmic radio sources generally spread their energy across broader frequencies, yet no confirmed extraterrestrial origin followed from that observation. Scientists needed repetition. It never came. Researchers returned to the same region with increasingly sensitive instruments. Numerous searches followed across decades, yet the original signal has never been detected again. Proposed explanations have included terrestrial interference, unusual astronomical phenomena, and emission associated with hydrogen surrounding comets. None has achieved universal acceptance as a definitive solution. The source direction pointed toward Sagittarius, along a line of sight crowded with stars near the broader direction of our galaxy's center. That density matters. When you look through such a populated region, apparent alignments become easier to find purely by chance. In 2025, Harvard astrophysicist Avi Loeb discussed another curious alignment involving the interstellar object 3I Atlas. Its incoming direction appeared within roughly 9 degrees of the general sky region associated with the WOW signal. Loeb estimated a chance probability of approximately 6/10 of 1% under assumptions used in his analysis. That number requires caution. A low probability for one selected alignment does not establish a physical connection. The sky contains countless objects, directions, and historical observations from which coincidences can emerge. 3I Atlas has provided no confirmed evidence connecting it to the WOW signal, extraterrestrial technology, antimatter, or any civilization. Yet the coincidence remains interesting precisely because we can separate curiosity from conclusion. For more than 40 years, one brief radio event has resisted a universally accepted explanation. We possess the original measurement, its duration, frequency, and approximate direction. Beyond those facts, certainty disappears. Perhaps that is what gives the WOW signal its lasting place in astronomy. It reminds us that our listening has covered only a fraction of the electromagnetic spectrum across an almost unimaginably brief interval of cosmic history. Sometimes the universe gives us an answer. Sometimes it gives us a data point and leaves us with the discipline to admit that we still do not know. Planetary defense is built around categories. We watch asteroids, model volcanic systems, study stellar explosions, and map the consequences of rare cosmic events. Each threat follows different physics, yet most provide some combination of warning, protection, recovery, or intervention. A hypothetical antimatter impact occupies an unusual position because several of those advantages could disappear together. Consider an ordinary asteroid large enough to threaten civilization. Modern surveys can sometimes identify dangerous objects years or decades before a potential encounter, although warning times vary greatly. Once an orbit is known, intervention becomes conceivable. The double asteroid redirection test demonstrated in 2022 that a kinetic impactor can measurably alter an asteroid's motion. With enough warning, even a tiny change can accumulate across millions of miles. Other catastrophes allow almost no preparation. A nearby gamma-ray burst would send its radiation toward Earth at the speed of light. We would receive no advance warning from the burst itself. Depending on its distance and orientation, intense radiation could alter atmospheric chemistry and damage the ozone layer, increasing harmful ultraviolet exposure afterward. Yet the initial astronomical event would pass rapidly. Humanity would then confront consequences unfolding across the planet. Supervolcanoes belong to another category. Their eruptions can devastate enormous regions and inject particles into the atmosphere, disrupting climate for years. The Toba eruption, roughly 74,000 years ago, was among the largest known eruptions of the recent geological past. Earlier claims that it reduced humanity to only a few thousand individuals remain debated, but our species survived the event and its environmental aftermath. An antimatter object combines different problems. For a sufficiently small, fast incoming body, recognition might come late. Energy release would begin during atmospheric entry as annihilation occurred against surrounding matter. Gamma radiation could penetrate materials that offer useful protection against heat or blast effects. Ionization across the atmosphere might also disturb communications and electronics, although the exact scale of any electromagnetic effects would depend strongly on the object's mass, trajectory, altitude, and annihilation dynamics. Then comes the interception problem. Conventional asteroid deflection assumes that a spacecraft can physically strike its target. A matter spacecraft contacting an antimatter body would instead annihilate at the point of contact. That interaction would transfer energy and momentum, so interception would not automatically be useless, but designing a predictable deflection would become extraordinarily difficult. Remote methods involving directed energy or other non-contact forces remain speculative and untested for this scenario. No dedicated planetary defense architecture currently exists for such an object. That absence needs context. Antimatter impactors remain hypothetical, with no confirmed antistar, anticomet, or antimatter asteroid known to threaten Earth. Existing defense programs concentrate on hazards supported by direct observational evidence and measurable populations. Still, this thought experiment exposes something useful. Planetary defense depends upon knowing what we are looking for. Asteroids became manageable targets only after we learned to discover, track, and predict them. An antimatter object would challenge that sequence at every stage, leaving us with a threat whose defining difference is not simply its destructive energy, but how little of our existing defensive framework was designed to recognize or confront it. Tunguska offers a lesson that reaches beyond the object itself. It shows how difficult astronomy becomes when the evidence arrives once, destroys its source, and leaves investigators to reconstruct an event from consequences scattered across the ground. Today, the leading explanation is a natural cosmic impactor. A stony asteroid, perhaps roughly 160 to 260 feet across, entered Earth's atmosphere and underwent a powerful airburst several miles above Siberia. No intact body needed to strike the surface. That conclusion emerged gradually. Researchers mapped the radial pattern of fallen trees across the devastated region. Later investigations examined microscopic particles preserved in local soils and peat, searching for chemical and mineral signatures consistent with extraterrestrial material. Increasingly sophisticated computer simulations then tested whether an ordinary asteroid could reproduce the blast effects without creating a conventional impact crater. Together, those lines of evidence made the natural airburst explanation compelling. But the historical record exposes a different problem. Imagine standing beside the instruments available in 1908. There were no orbiting gamma-ray observatories watching the atmosphere. No global network continuously recorded every energetic transient. When Leonid Kulik reached the region in 1927, nearly 2 decades had already passed. Even by 1965, the evidence remained incomplete enough for serious physicists to consider antimatter. Clyde Cowan, Chandra Raghava Rao at Lurie and Willard Libby published an antimatter interpretation in Nature, attempting to explain the immense energy release alongside the absence of a conventional crater and large surviving fragments. Their proposal ultimately proved unnecessary, yet eliminating it required evidence unavailable to the earliest investigators. That is the forensic paradox. An ordinary airburst and a hypothetical antimatter airburst can both produce tremendous atmospheric energy without leaving an intact impactor. Distinguishing between them depends on identifying what kinds of radiation were emitted, what microscopic material survived, and whether the energy deposition matches ordinary fragmentation or annihilation physics. If such an event occurred today, our position would be better. A sufficiently large antimatter airburst should generate distinctive high-energy radiation detectable by suitable space-based instruments, provided they were observing the correct region with adequate sensitivity. Ground networks would record pressure waves. Satellites might capture atmospheric disturbances, optical flashes, and other signatures. The global infrasound system demonstrated its reach after the Chelyabinsk meteor exploded over Russia in 2013. Stations, thousands of miles away, detected its atmospheric pressure waves. An antimatter event could also generate infrasound, but pressure measurements alone would reveal energy and location, not necessarily the physical identity of the incoming object. For smaller events, ambiguity could remain. A compact object annihilating high in the atmosphere might produce a brief energetic transient whose interpretation depended entirely on whether the right instruments recorded it. Missing radiation data could leave investigators with only a flash, a pressure wave, and atmospheric effects. So when we look back at Tunguska, the deeper mystery is no longer what probably happened there. It is what our instruments allow us to distinguish. Somewhere within the enormous archive of atmospheric explosions, rare transients, and unexplained detections, an unusual event could hide beneath an ordinary label simply because we never collected the one measurement needed to tell them apart. For more than 16 years, the sky has been examined in a form our eyes cannot perceive. Since June 2008, the Fermi Gamma-ray Space Telescope has repeatedly surveyed the entire celestial sphere, recording high-energy events and building an increasingly detailed map of the gamma-ray universe. That long record matters here. The Large Area Telescope, aboard Fermi, has cataloged thousands of gamma-ray sources, yet none has revealed the moving trajectory expected from a substantial antimatter object crossing the inner solar system. No identified source has steadily brightened in the pattern anticipated as such an object approached the Sun and encountered progressively denser, ordinary matter. This is genuine observational evidence. A sufficiently massive antimatter body nearby should interact continuously with the solar wind and surrounding particles. Those annihilations would generate high-energy radiation. As the object moved inward, increasing particle density should strengthen that emission, creating a source whose changing position and brightness could potentially be tracked. We do not see one. The 14 antistar candidates identified in the 2021 analysis present a very different picture. They appear as fixed celestial sources rather than nearby bodies traversing the solar system. If any ultimately prove to be antistars, their apparent positions remain consistent with distant astronomical objects, not immediate visitors moving toward Earth. The interstellar objects we have actually observed reinforce that distinction. Oumuamua, discovered in 2017, crossed the solar system on an unbound trajectory. 2. I. Borisov followed in 2019 and displayed clear cometary activity. 3. I. Atlas, discovered in 2025, became the third confirmed interstellar object known to pass through our planetary neighborhood. Each entered our records through ordinary astronomical observation. None produced a confirmed gamma ray signature indicating matter and antimatter annihilation. Their observed behavior has remained consistent with bodies composed of ordinary matter, even when individual properties prompted scientific debate. Our ability to find future visitors is also improving. The Vera C. Rubin Observatory is designed to repeatedly image the southern sky with exceptional depth, allowing astronomers to discover changing and moving objects far more efficiently. Combined with existing surveys, its observations can narrow important gaps in our awareness of interstellar bodies entering the solar system. So, what does the evidence actually allow us to say? Within the sensitivity of present instruments, there is no detected antimatter object approaching Earth. There is no moving gamma ray source behaving like an anticomet. There is no observed pattern suggesting that a massive antimatter body is currently descending through the inner solar system. Science rarely offers absolute certainty about what has never been observed. Instruments have sensitivity limits. Surveys contain gaps. Small or distant objects can escape detection, but evidence still carries weight. If a large antimatter threat were already nearby, physics predicts signatures that our instruments should have a reasonable chance of detecting. Those signatures are absent. As you look across the accumulated observations, the picture becomes reassuringly consistent. Every confirmed interstellar visitor has behaved like ordinary matter, while the gamma ray sky shows no known approaching antimatter source. For now, that is where the measurements leave us. The possibility remains within physics, but the danger is absent from the data we actually possess. There is a particular moment in science when an answer becomes a boundary. Beyond it lies something measurable in principle, permitted by physics, yet still beyond the reach of observation. The boundary moves whenever our instruments improve. What remains beyond it changes with every discovery. We often imagine scientific progress as an expanding collection of answers. In practice, it also produces an expanding map of uncertainty. The more precisely we measure nature, the more clearly we identify what remains unresolved. A century ago, that map looked profoundly different. Astronomers had not yet established the expanding universe. The true nature of galaxies beyond the Milky Way was only beginning to emerge. Humanity lacked a reliable age for the cosmos. The molecular structure of deoxyribonucleic acid remained unknown. Antimatter itself existed only as a consequence, waiting inside equations that physicists had yet to interpret fully. Then the boundaries moved. Each discovery answered something fundamental, while exposing another layer beneath it. Galaxies revealed a universe larger than expected. Cosmic expansion raised questions about origins and ultimate fate. Antimatter transformed mathematical symmetry into physical reality, then left us confronting one of cosmology's deepest mysteries. Why does the observable universe contain overwhelmingly more matter? Our journey through the possibility of antistars belongs to that same process. We know antimatter exists. Established physics allows stars composed of it. Gamma ray observations have identified intriguing candidates, although none has been confirmed as an antistar. The mathematics of annihilation allows us to calculate what contact between large quantities of matter and antimatter would produce. Eventually, however, calculation reaches observation's frontier. Are there antimatter objects nearer than our instruments can presently identify? We cannot provide a definitive answer. Current evidence offers reassurance, while sensitivity limits preserve a narrow region of uncertainty. That distinction matters. Saying we have not detected something differs fundamentally from proving that nowhere remains for it to exist. This is how science works at its edge. History repeatedly shows us a universe larger, older, and more intricate than earlier generations could demonstrate. Ideas once considered unnecessary sometimes return when new instruments reveal unexpected data. Others disappear permanently under stronger evidence. Science advances by allowing both outcomes. The antimatter interpretation of Tunguska became unnecessary once ordinary explanations grew stronger. Antistars remained largely theoretical possibilities for decades. Then observations from the Fermi Gamma-ray Space Telescope produced 14 candidate sources worthy of investigation. They did not prove antistars exist. They simply changed what could reasonably be examined. That difference is the heart of scientific uncertainty. You do not need to believe that an antimatter object is approaching Earth. The available evidence gives us no reason to think one is. Almost certainly, this particular scenario will remain hypothetical. But when we follow the reasoning honestly, we encounter something more enduring than any single threat. We discover the asymmetry between what physics permits and what astronomy can currently observe. Our knowledge has edges. We can measure some of them. Beyond those edges lies an unknown whose size we cannot yet calculate, containing possibilities awaiting better instruments, longer observations, and discoveries for which we may not yet have names. The carbon within your body carries a history older than Earth. Long before the sun existed, earlier generations of stars forged carbon through nuclear fusion, then returned that material to space through stellar winds and explosive deaths. Gravity gathered some of those scattered atoms into a new system. Eventually, they became planets, oceans, living cells, and you. Yet, the deeper story begins earlier still. In the first moments after the universe began, matter and antimatter existed in almost equal amounts. When opposing particles met, they annihilated, transforming their mass into energy. Somehow, matter possessed a minute advantage. For roughly every billion antimatter particles, physicists think there may have been about 1 billion and 1 matter particles. That tiny imbalance changed everything. After the great annihilation ended, the small residue of matter remained. From that surplus came hydrogen and helium, then stars. Inside those stars, heavier elements formed, galaxies assembled, planets emerged. Chemistry grew complicated enough for biology, and biology eventually produced minds capable of reconstructing events that occurred billions of years before minds existed. You are part of that residue. Every thought you have is carried by matter that survived because of an asymmetry whose origin remains unknown. The fact that this matter can now study itself adds another layer to the mystery. Atoms once drifting through ancient stars have become organized enough to build observatories, develop mathematics, and ask why there are atoms at all. As far as we currently know, humanity represents one place where the universe has become capable of examining its own history. Through us, matter investigates the conditions that allowed matter to remain. We search the galaxy for the mirror substance that nearly balanced us away, wondering whether entire stars made from antimatter might still exist beyond our certainty. The investigation reaches across scales almost impossible to reconcile. The Fermi Gamma-ray Space Telescope watches high-energy radiation crossing immense distances. The Cherenkov Telescope Array Observatory seeks traces of energetic processes in the cosmos. Papers in Physical Review D turn mathematical possibilities into predictions that observations can test. These efforts serve purposes far broader than planetary defense. They belong to one of the oldest human pursuits, understanding what reality is made from and why it took this particular form. There is something extraordinary in the arrangement. Matter survived the earliest universe by an exceedingly small margin. Some of it gathered into stars, where new elements were forged. Those elements traveled through space, entered another planetary system, and became living organisms. Eventually, one species learned to shape glass into mirrors, construct particle detectors, and translate distant radiation into knowledge. Now we look outward, searching for the counterpart that disappeared from our surroundings. We are matter, asking why matter exists. We are the surviving side of an ancient imbalance, trying to understand the symmetry that came before us. And when you consider the entire chain, the antimatter question becomes more than a calculation about destruction. It becomes a question about why there was ever anyone here to make the calculation. Probability changes the shape of a danger without changing its physics. An antimatter object striking Earth would remain an extreme event in any calculation. Yet the chance that such an object is approaching us now appears extraordinarily small, even compared with other cosmic hazards already considered remote. That distinction gives the numbers their proper scale. Ordinary asteroids large enough to threaten civilization are actively monitored, and none currently known presents a significant near-term impact danger. An antimatter impact requires additional layers of improbability. Antimatter must exist in macroscopic form, survive immense stretches of space, enter our solar system, evade detection, and intersect Earth's orbit at precisely the right moment. Every requirement narrows the possibility further. Observations reinforce that conclusion. Data from the Fermi Gamma-ray Space Telescope suggests that antistars, if the candidates ultimately prove genuine, are rare and distant. Survival calculations indicate that large antimatter bodies moving through the solar system should interact with surrounding matter and produce detectable radiation. For more than 16 years, Fermi has watched the gamma-ray sky. No anomalous moving source has appeared with the behavior expected from an approaching antimatter object. Absence alone cannot prove universal safety, but sustained observation where a detectable signature should exist carries genuine evidential weight. So we can hold two ideas together. The consequences of a large antimatter impact could be extraordinary. The probability of experiencing one appears vanishingly small. Understanding both allows us to see the scenario at its full dimensions without enlarging the likelihood simply because the consequences are immense. There is reassurance in precision. The universe operates according to physical laws that do not consult our hopes or fears. Gravity gathers matter. Stars ignite. Particles collide. Radiation crosses interstellar distances. None of these processes carries intention toward us. They simply unfold according to conditions established by nature. Those same laws permit remarkable possibilities. Perhaps somewhere across the galaxy, antistars truly exist. Around some of them, antiplanets might orbit beneath unfamiliar constellations. If complexity arose there, perhaps beings made entirely from antimatter eventually developed physics and confronted their own version of this calculation. They might look outward toward a galaxy containing dangerous islands of ordinary matter. Their instruments might search for annihilation, radiation. Their scientists could estimate distances, calculate probabilities, and conclude that the separation between those distant regions and their home is overwhelmingly likely to protect them. We may never know. The scale of the cosmos permits possibilities beyond ordinary imagination while placing enormous distances between them. Something can be physically possible and still remain so remote that entire civilizations could rise and disappear without ever encountering it. Tonight, Earth continues along its familiar orbit. The atmosphere remains above us. Our detectors reveal no antimatter object approaching through the inner solar system. The available observations contain no indication of an immediate threat. And you remain here, made from the ancient surplus that survived the beginning, beneath a universe whose immense distances can sometimes be their own form of protection. Measured against a human lifetime, the future seems almost limitless. Measured against the sun, our entire recorded history occupies less than an instant. We have arrived during one narrow interval in a cosmic story, already 13.8 billion years old, with transformations still waiting across timescales beyond ordinary intuition. Earth itself has limits. In roughly 1.1 billion years, the gradually brightening sun is expected to make our planet increasingly hostile to complex life. Rising solar energy will accelerate changes in the atmosphere and oceans. Eventually, Earth's present habitability will end, regardless of asteroids, antimatter, or any other external hazard. The sun will continue aging. Around 5 billion years from now, hydrogen in its core will become exhausted. Its internal structure will change, and the sun will expand into a red giant, profoundly transforming the inner solar system. Earth may be engulfed or rendered entirely unrecognizable long before the sun sheds its outer layers. What remains will become a white dwarf, an extremely dense stellar remnant, roughly comparable to Earth in size. It will contain much of the sun's former mass and slowly release stored heat across immense spans of time. Long after familiar planets have vanished or frozen, that remnant could persist for trillions of years. Against such a horizon, improbable dangers assume different proportions. Our solar system has already existed for about 4.6 billion years. During that interval, Earth endured 5 recognized mass extinctions, numerous impacts, dramatic climate transitions, and changing conditions within the Milky Way. The Sun has traveled around the galactic center repeatedly, carrying its planets through environments of varying stellar density and radiation. Still, Earth remained. Whatever objects occupy the distant Oort cloud, and whatever unseen bodies wander between stars, our planet has navigated cosmic history without requiring protection from most conceivable encounters. Large distances and low probabilities have done much of the work. Across billions of years, countless possible trajectories simply never intersect. But some events require no probability calculation. Stellar evolution is already determining Earth's distant future. The sun is changing now, although far too gradually for any human observer to notice directly. Its eventual transformation follows physical processes established long before humanity appeared. We occupy a remarkably brief interval between those immense boundaries. For the first time in Earth's known history, matter on this planet can reconstruct the age of the universe. We can calculate the future of our star, trace planetary history backward, and identify forces capable of ending worlds. We can even consider hypothetical objects that may never come near us. That ability exists now. For 4.6 billion years, Earth circled the sun without understanding what either one was. Then, during a tiny fraction of planetary history, living beings emerged who could measure stars, recognize antimatter, and calculate futures billions of years beyond their own lives. We may be the only moment in this solar system's history capable of doing so. And for however long that moment lasts, the universe has something within it that can look outward, look backward, and understand where it stands in time. Suppose there is a star whose light reaches our telescopes tonight. Its spectrum resembles that of an ordinary star. Gravity gathers its planets into familiar orbits, while radiation warms distant surfaces beneath its glow. Yet every particle within that system may belong to the mirror side of nature, assembled from antimatter rather than the matter surrounding us. From across light years, the distinction almost disappears. An antistar would shine through the same fundamental processes that illuminate ordinary stars. Around it, worlds could form from disks of material, settling into layered interiors and evolving across billions of years. Some might possess atmospheres, others could carry oceans beneath changing skies. Seasons might follow tilted axes, while weather moves energy across continents we will never map. Chemistry could continue the story. If the requirements for life depend on molecular complexity, usable energy, and stable environments, antimatter offers no obvious prohibition. An anti-world could experience its own long biological history. Simple organisms might diversify. Evolution could explore possibilities shaped by local conditions, extinction, competition, and chance. Perhaps complexity would eventually look upward. From such a world, our galaxy would appear familiar. Its astronomers could measure stellar motions and reconstruct cosmic history. Their mathematics might reveal a strange mirror substance predicted by physical law. In their laboratories, tiny quantities of ordinary matter could become the exotic material, dangerous precisely because contact with their surroundings releases energy through annihilation. Then the symmetry becomes almost complete. We could exchange light with such beings. Photons can cross the divide, carrying information without requiring physical contact. A signal might travel between civilizations whose spacecraft could never safely meet. Knowledge could cross where bodies cannot. The barrier is fundamental. Matter and antimatter meeting directly annihilate each other, converting their mass into other forms of energy. Neither side receives special protection. Physics treats both equally. The boundary between them therefore contains no victor, only the same consequence viewed from opposite directions. But the enormous distances that make contact remote also make accidental encounters extraordinarily unlikely. The separation itself becomes protection. Space places immense intervals between stellar systems, reducing the probability that wandering material from one domain will ever reach another. You can see the strange balance within that arrangement. The same laws allowing a mirror world also prevent us from touching it safely. The distances that deny physical contact reduce the danger of collision. Isolation and protection emerge from one structure, inseparable from each other. For now, the mirror exists only as possibility, mathematics, and unresolved observation. 14 candidate signatures remain points in astronomical data, awaiting stronger evidence and better instruments. Paul Dirac's equations still describe the symmetry that first opened this door in physics. Perhaps those candidates will eventually receive ordinary explanations. Perhaps one will prove extraordinary. Either way, we remain here, made from one surviving form of matter, receiving ancient light across distances no hand can cross. The mirror may exist beyond our reach, and our inability to touch it may be precisely what allows both sides to endure. Home becomes easier to overlook precisely because it surrounds us. We wake beneath an atmosphere, walk across a differentiated planet, and orbit a stable star without needing to consider the machinery involved. Yet follow the antimatter thought experiment far enough, and familiar surroundings begin to look different. The calculation eventually returns us to Earth. This world has retained surface oceans for billions of years. Its large moon helps limit extreme variations in axial tilt over long timescales. Deep below us, motion within the electrically conducting outer core sustains a global magnetic field, deflecting much of the charged particle flow arriving from the Sunday. Farther outward, Jupiter's enormous gravity alters the trajectories of comets and asteroids, sometimes redirecting objects and sometimes sending them inward. Above everything lies the atmosphere. Every square foot of ground at sea level supports roughly 2,100 pounds of atmospheric weight. Gravity holds that immense column around the planet, while geological cycles and biological activity have transformed its composition across deep time. The result is something we experience simply as air. Its work extends far beyond breathing. Atmospheric pressure helps keep liquid water stable across much of Earth's surface. Ozone in the upper atmosphere absorbs much of the sun's damaging ultraviolet radiation. Greenhouse gases regulate surface temperature, while circulation redistributes heat around the globe. Together, these conditions allow complex chemistry to persist across continents and oceans. The atmosphere is also our first planetary defense. Ordinary meteoroids enter it continually. Frictional processes and compression of air ahead of them generate intense heating, breaking apart or vaporizing many before they reach the surface. Larger objects can survive deeper, sometimes producing airbursts or impacts, but countless smaller visitors disappear overhead without consequence. An antimatter object would encounter an even stranger version of this protection. Contact with atmospheric matter would trigger annihilation along its path. For a sufficiently small object, that interaction could consume much of it high above the ground, releasing energy into the surrounding atmosphere rather than allowing an intact body to strike the surface. The same air that sustains you would become the first material it met. There is an unexpected symmetry here. A substance imagined as our vulnerability reveals the strength of the environment already protecting us. The atmosphere does not distinguish between ordinary cosmic debris and hypothetical antimatter. It simply presents an enormous barrier of matter between space and the surface. We rarely notice that barrier because it has always been here. For roughly 4 billion years, Earth's surface has maintained environments where liquid water could persist, even as the atmosphere itself evolved dramatically. Life eventually became part of that evolution, reshaping atmospheric chemistry while depending upon the protection that atmosphere provided. So, the antimatter calculation leaves us somewhere familiar. You are standing beneath a planetary shield measured in thousands of pounds above every square foot, sustained by gravity, geology, sunlight, and life. We call it the sky. Only after doing the calculation do we remember what the sky has been doing all along. Before there were stars, planets, oceans, or living cells, the universe passed through an imbalance almost too slight to imagine. For roughly every billion pairs of matter and antimatter, one additional particle of matter remained. The pairs met and annihilated. The surplus endured. Everything familiar begins there. One particle among a billion sounds negligible when spoken aloud, yet multiplied across the newborn universe, that tiny excess became the material inventory from which cosmic history could proceed. Had the imbalance favored antimatter instead, a mirror cosmos might still have formed galaxies, stars, planets, chemistry, and perhaps living systems. But none of it would be us. The universe made no choice between these possibilities. As far as physics can determine, The imbalance emerged from processes connected to broken symmetries in nature, subtle differences that allowed matter and antimatter to behave unequally under particular conditions. Scientists can describe parts of this problem mathematically. Its complete explanation remains unknown. From that unresolved beginning, the remainder expanded with space. Gravity gathered matter into the first stars. Their interiors forged heavier elements, and stellar deaths scattered those elements outward. New generations formed from enriched clouds. Around one ordinary star, a disk assembled into planets, chemistry became increasingly elaborate. On Earth, molecules began reproducing, evolution accumulated complexity, and eventually, matter acquired the ability to examine the history that produced it. You belong to that sequence. Every person you have known is made from the remainder. Every human voice, every written sentence, every piece of music, and every memory carried through a lifetime depends upon matter surviving that earliest cancellation. So does every telescope raised toward the sky. The chain extends across 13.8 billion years. Expansion allowed the universe to cool. Stars illuminated the growing darkness. Galaxies assembled and changed. Elements passed through generations of stellar interiors before becoming worlds, atmospheres, oceans, organisms, and minds. At no stage was the destination guaranteed. The initial imbalance did not contain a blueprint for humanity. It simply left something available for gravity, nuclear physics, chemistry, and time to transform. From that surviving fraction came every structure we can observe and every instrument with which we observe it. Look outward, and the remainder fills your view. It is present in distant galaxies whose light began traveling before Earth existed. It forms the stars scattered across the night. It makes the planets moving around them, the ground beneath you, and the eyes receiving their ancient photons. The deepest mystery remains untouched. Why did anything survive? Physics has narrowed that question into something remarkably specific. Somewhere in the earliest conditions of the universe, matter gained the smallest advantage. The reason is still incomplete, but its consequence surrounds us completely. There was almost perfect cancellation. Almost. Something remained. That remainder became everything we can see. And for this brief moment in cosmic time, part of it became you. Across the sky, an observation is being repeated once again. The Fermi Large Area Telescope scans for gamma rays, registering high-energy photons that have crossed immense distances before reaching its detectors. Each pass adds another layer to a record, extending back more than 16 years. The measurements accumulate slowly. Sources become better defined. Uncertainties narrow. Patterns emerge from years of repeated observation, while unusual signals can be compared against an increasingly detailed history of the gamma-ray sky. Somewhere within that enormous archive sit 14 sources identified as possible antistar candidates, still awaiting explanations strong enough to settle what they are. Other instruments watch differently. On mountain sites in Chile and the Canary Islands, Cherenkov telescopes study brief flashes produced when energetic particles strike Earth's upper atmosphere. Cherenkov radiation is the faint light generated as secondary particles race through the atmosphere faster than light travels through that medium. Those flashes allow astronomers to reconstruct events originating far beyond Earth. Meanwhile, the Vera Rubin Observatory surveys the southern sky with extraordinary depth. Its repeated observations are designed to reveal change. Objects shift position. Stars vary in brightness. Asteroids trace new paths between exposures, Anything appearing where nothing was recorded before becomes part of an immense stream of astronomical information. None of these instruments understands what it sees. They possess no expectation that an antistar exists somewhere beyond us. They cannot wonder whether an interstellar object is ordinary matter or something stranger. Mirrors collect photons, sensors register energy, computers compare measurements. Mathematics turns those measurements into coordinates, spectra, trajectories, and probabilities. We supply the questions. Behind every telescope stands a long chain of people who designed detectors, calibrated instruments, developed software, interpreted signals, and challenged interpretations. Some have examined the possibility that antimatter survived in isolated regions of the cosmos. Others have searched for conventional explanations of the same observations. That disagreement is part of the process. 14 candidates remain candidates. They are neither confirmed antistars nor meaningless anomalies. Their existence in the catalog simply marks places where available data permits an unusual interpretation that further observation may eventually strengthen or remove. But another measurement matters just as much. No gamma ray source has been observed, tracing the unmistakable path of a large antimatter object approaching the inner solar system. No growing annihilation signature has appeared where such an object should become increasingly visible. Our instruments have searched across years, and the expected evidence of immediate danger has remained absent. That absence carries information. It cannot prove that every corner of nearby space contains ordinary matter. Science rarely grants conclusions that absolute. It can tell us what the best available observations support today, while preserving room for tomorrow's measurements to revise the picture. For now, you can rest beneath a sky being measured more carefully than at any earlier moment in human history. The detectors continue their work. The catalogs continue growing. We continue learning where uncertainty remains. And tonight, the instruments are still listening. The Milky Way stretches across roughly 100,000 light years, a vast disk of stars separated by distances that human intuition was never built to hold. Seen from Earth, those distances collapse into points. Yet every point occupies its own island of space, divided from the next by reaches so immense that light itself requires years, centuries, or millennia to cross them. Beyond the planets lies another boundary. The distant outer reaches associated with the Oort cloud extend so far from the Sun that light may take more than a year to traverse the greatest estimates of its span. Even there, we remain inside the gravitational domain of our star. Farther out, the distances deepen. Somewhere beyond that boundary may exist the objects we have spent these hours considering. Perhaps 14 unusual gamma ray sources represent antistars. Perhaps future observations will reveal ordinary explanations. There may be antiplanets circling distant suns, or smaller fragments wandering between stellar systems, carrying histories we cannot reconstruct. Between those possibilities and you lies an extraordinary expanse. Interstellar space contains matter, though astonishingly little of it. Hydrogen and helium drift between stars. Dust grains cross the galaxy. Cosmic rays move through magnetic fields, while ancient photons travel onward from sources whose present state we may never witness. Light from distant galaxies passes through these regions in every direction. Still, the separation remains enormous. That distance is part of the physics. An object crossing interstellar space must travel through a domain where destinations are separated by light years, while stars themselves occupy only tiny fractions of the volume around them. Encounters can happen. The equations allow them, Yet possibility and proximity are profoundly different things. So the threat we followed through mathematics remains where the evidence places it. Antimatter exists. Larger structures made from it may exist. Matter and antimatter annihilate when they meet, releasing energy according to laws tested repeatedly in laboratories and observed throughout high energy astrophysics. But tonight, there is no known antimatter object approaching Earth. No growing gamma ray source traces a path toward the Sunday. No detected interstellar visitor carries the signature expected from sustained annihilation with surrounding matter. Above you, Earth's atmosphere remains intact, while observatories continue measuring the universe with instruments more sensitive than any previous generation possessed. And beyond them stretches the dark between the fires. If antistars truly burn somewhere across the galaxy, their light crosses distances measured in centuries and millennia before reaching our detectors. We see them only after space has carried their photons toward us across an ocean no spacecraft has crossed. For now, distance holds. The stars remain where gravity carries them. The planets continue along their paths. The instruments continue watching, and the laws describing matter remain unchanged. You are still here beneath them. The sky is still there. The mathematics still works. And the remainder is still here.